A very good morning to everyone in New York and very good evening to everyone in India. I, Dr. R.P. Sugavaneshwar, heartily welcome our Vice Chancellor, Dr. U. Kamachi Modli, our Registrar, K.K. Nair, and our Dean Academics, Dr. Manas Kumar Mishra, all deans and program chairs, and my faculty colleagues and student members to this first webinar from Binghamton University, delivered by Dr. Mohammad Kashavne on healthcare systems engineering, operation management, and data science. We indeed appreciate the overwhelming response for and enthusiasm to register for this first webinar from the Binghamton University. We really received an enormous number of registration for this webinar. And before I would proceed, I would like to say a few words about our memorandum of agreement with the Binghamton University. VIT BHOPAL and Binghamton University has entered into a memorandum of understanding to establish a new academic and research cooperation between them. And we heartfully thank our management, Chancellor, Dr. G. Vishwanathan, and our Vice President, Mr. Shankar Vishwanathan, and our Assistant Vice President, Ms. Kadambari S. Vishwanathan, for their encouragement and support in establishing this memorandum of agreement. And as a part of this memorandum of agreement, this will be the first of the series of webinars which we are organizing between the Binghamton University and VIT Bhopal. And with this one, I would like to take the privilege to introduce our distinguished speakers for today, Dr. Mohammad Kashavne. Dr. Mohammad Kashavne is a professor and chair of system science and industrial engineering at Binghamton University, and he received his PhD in industrial engineering from Clemson University and his BS and MS in mechanical engineering from Jordan University of Science and Technology. Dr. Kashavne research is focused on healthcare systems engineering, operation management, and data science, and he currently serves as the director of Watson's Institute for System Excellence and Institute for Advanced Studies that generates $3+ million research fund annually. And he also serves as the founding director of the Healthcare Systems Engineering Center and Research Center at Binghamton University. Over the years, Dr. Kashavne has presented his various research at national and international conferences in various countries, and his activities thus far include 65 referred journals and 144+ conference articles and 1 patent and 3 new invention disclosures. In addition to his sponsored research efforts to date have resulted in $12 million in external funding and over $39 million in software equipment and grants. In his illustrious career, Dr. Kashavne has received numerous recognition, including a U.S. Air Force summer faculty fellowship and a fellowship from U.S. Air Force Office of Scientific Research, and recipient of State University of New York's Chancellor's Award for Excellence in Teaching, University Award for Outstanding Graduate Director, and he also holds an honorary visiting professor in Industrial Engineering Department in Hebei University of Tianjin and School of Mechanical Engineering at Vellore Institute of Technology, Vellore, India. So we are really actually privileged to have such a wonderful speaker among us, and we are privileged to hear him today about the topic on healthcare. So over to you, Professor.
Thank you. Thank you very much, Dr. Sugo, for the kind introduction. I would like to start by thanking the Vice Chancellor for joining us today and kicking off this event. It's definitely a great pleasure to be with you, sir, and with Dr. Sugo. I'd also like to thank all the deans, the registrar, the department heads, the faculty, and the students for joining us today to attend this webinar on a topic that is very dear to my heart, which is healthcare systems engineering, because of the impact it could have on each and every one of us, our families, friends, the community in which we live, and most importantly, around the globe. Especially because of the recent pandemic, the role of systems engineering in healthcare has become more than ever before a very crucial part of the operations at healthcare systems around the globe. So with that, I would like to go ahead and start my presentation. If you have any questions at any time, please feel free to post them in the chat, and at the end we will have time for details, questions, and answers. So this is the first portion of my presentation, just to give you a high-level overview about system science and industrial engineering, and our international partnerships around the globe, specifically in India. And next, I will start talking about the current state of the healthcare system, specifically in the US, but I can assure you that this information is applicable to healthcare systems around the globe. I got the chance to visit hospitals in Pune, India. I visited Sri Ramachandra in Chennai. I visited some of the PSG hospitals in Coimbatore. And I got to visit hospitals in Andhra Pradesh in various places to talk to them about, industrial engineering, quality management, lean, Six Sigma. And I got to learn a lot about the healthcare system in India and the role of industrial and systems engineering. So I can assure you that this knowledge is transferable to many domains. And I would like to start with the slide just to tell you about the complexity of the healthcare system today. This is what we call a patient journey map. This basically shows the journey of a heart attack patient from the time they enter the emergency department until they are discharged from the hospital. And if you just take a minute to count the number of people that are involved in the patient care process. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And maybe at the discharge, someone else is involved, but let's say 18 individuals. Just imagine the patient flow process. Just imagine the information that is generated at every interaction, or what we call every touch point in this process. Just imagine the amount of information that will be generated, that will be transferred from one step to another. Just imagine the amount of time each one of these takes. If you think about healthcare, almost a century ago, we did not have this many people involved in the patient care process. It was just on average about 2 individuals involved in the patient care process. Today, healthcare has become very complex, very specialized. Just within surgery, we have so many specialties. So healthcare has become what we call a complex system that is very difficult to manage, very difficult to optimize, very difficult to improve. So in terms of the number of people involved, healthcare is a complex system. In terms of information services and hardware and software, there are many types of software and hardware systems in hospitals, and information systems for billing, for pharmacy, for labs, for cost accounting, for safety, for the emergency room, operating room, the ICU, outpatient clinics, registration. And unfortunately, in many cases, those systems do not talk to each other. We truly do not have a unified, enterprise-wide information system that can interact with each one of these information systems. On average, at US hospitals, there are usually more than 100, 150, 200 plus different types of software programs. So that adds to the complexity of the healthcare system in terms of the number of information systems that are available. So again, complexity in terms of the number of people, complexity in terms of the software and hardware involved. And most importantly, the interoperability of these devices continues to be a challenge. So that's why systems engineering can help us address these complexities and make the system very efficient and effective. This system right now has many bottlenecks. That's why for those of you who are mechanical engineers and are familiar with Lean, Six Sigma, and quality management, you can very easily study this flow, this journey map, and look for bottlenecks and try to find out ways to improve the system. I will pause on this slide for about 30 seconds and just give you the 30 seconds to absorb what this slide is actually trying to tell us. And I'm sure that by the moment you finish reading the slide, you will be scared. Which is sad. Because if you look at the slide, in the late 1990s, in the US, we found out as a country that more than 90,000 people die in the healthcare industry because of preventable medical errors. Millions get injured from what we call hospital-acquired conditions, infections, falls, different types of infections. We call it hospital-acquired or hospital-caused because those are things that you did not have when you showed up at the hospital. You show up to the hospital for a kidney stone, and then you end up with an infection. That's not an infection that you had when you showed up at the hospital doors. That's a condition you acquired during your stay in the hospital. If you ask the average doctor, what are the things that scare them the most? They would tell you that they're scared about becoming a patient themselves because they know about these mistakes. They know about these errors, operational inefficiencies, safety concerns. This is scary. There is no other industry that kills this many people. And in the US, there is significant transparency. This data is published, at the Hospital Compare website. It's a governmental website where all this data is posted, so people know. But in many places around the globe, this is not stuff that they would post on various platforms, websites, social media, and so on. But in the US, you'll see that. I'll give you an example. This is an example of a wrong kidney that was removed from a cancer patient. Surgery that was conducted on the wrong side. Just imagine, you show up to the hospital for surgery on your right knee, and they end up operating on your left knee. And they tell you, oh, we sincerely apologize for the inconvenience. We truly meant to operate on your right knee, but by mistake, we operated on your left knee. This is actually called a never event. This is an event that should never happen. And this is an event that insurance companies stopped paying hospitals for. You might be wondering, well, this is, this data is from 2008. This is like 12, 13 years ago. Just 2 days ago, I saw an example of a never event that happened in a hospital in the state of Ohio. In the US, about 2,000 of these take place each year. So this is not a small number. Yes, the US is a big country, but 2,000 is a large number. It's small, relatively speaking, but when it comes to the impact on these human beings, this is a very significant number. This is a real story. This patient actually marked his body to make sure that the surgeons operate on the right leg, because this individual knew about wrong side surgeries, knew about this as a never event, and he went into the surgery nervous about them possibly operating on his wrong leg. So he actually marked it to make sure that when they give him anesthesia and he's no longer awake, they don't end up operating on the wrong leg by mistake. And as you can see, doctors started laughing because this is not something that they expected. But I'm sure, those that come to this with an open mind realize that, this person knows and we need to be careful. This list, unfortunately, is endless. The list of possible mistakes: adverse drug events, surgical site infections, needle stick infections, wrong site surgeries, device-associated infections, ventilator-associated pneumonia, catheter and center line infections. Those are very serious events, and they happen quite a bit, and they cost a lot of money. A surgical site infection SSI can cost the hospital $14,000 here in the United States. A centerline associated bloodstream infection at our local hospital costs about $18,000. So just imagine the cost. And especially in the US, we as patients, we have insurance. I don't pay for this out of pocket. I pay a copay, we call it a copay, which is a small amount. I pay $20. When I go see the doctor, I either pay $20 or $25. The rest is paid by insurance company. I don't even know how much the insurance company pays. So now people might say, oh, you know what, the insurance company is going to pay for this, but no, not anymore. About 15 years ago, things started to change and insurance companies stopped paying hospitals for these because, again, if you think about each one of these, those are classified as hospital-acquired conditions. The patient did not show up with a surgical site infection at the hospital, but during surgery, they got infection. So who's going to pay for it? Now it's the hospital. So that's why hospitals today are hiring industrial engineers. Some of the hospitals we work with, they have more than 100 industrial engineers. And I tell my students, I've never seen a manufacturing company with 100 industrial engineers. But if you think about healthcare and the number of industrial engineers that specialize in process improvement, quality improvement, Lean Six Sigma, simulation, optimization, analytics, there is significant demand for industrial engineers to solve these problems. When these mistakes happen, we say, oh, to err is human. We are humans, we make mistakes. The Institute of Medicine in the United States, the National Academy of Engineers, they've studied these topics. And they've actually told us that, when you do scientific root cause analysis, we found out that these errors are due to poorly designed or broken care processes. Those are the reasons for these 90,000 plus deaths each year. It is not the human being. It's the environment in which the human beings function and these processes that are broken or poorly designed. So if you need to reduce human error, we need to improve the process design, fix the processes using systems engineering, systems thinking, systems problem solving, and so on. Some of you might be familiar with Six Sigma. Six Sigma, if you know Six Sigma, we have defects per million opportunities, DPMO, right? I think some of you might be familiar with this. Especially if you're a fourth year mechanical engineering student, you probably have learned about defects per million opportunities. A process that operates at Six Sigma produces around 3.4 defects per million opportunity. So on this axis, we want to be on the right-hand side. On the vertical axis, we want to be at the bottom of this axis because this is defects per million opportunities. So we want to be over here. So ideally, we want our system, our process to be in this region, at the lower right region. But if you think about the different industries, and this was published by GE Medical Systems, to compare Sigma levels at various industries. GE told us that the airline industry operates at a very high Sigma, which is good. Anesthesia during surgery, probably the only one in healthcare, operates at a good Sigma level as well, but everything else operates at a very low Sigma level, 3 to 4 Sigma level. 3 to 4 Sigma level is almost 100,000 mistakes. So if you think about it, if we talk about surgery, if you do 1 million surgeries and you only have 3.4 mistakes, so you can see it's very strict, quality standard. 3.4 errors during 1 million surgeries. But if the Sigma level is 3, this means that we have more than 100,000 mistakes during surgery. This is not acceptable. And what GE told us is that the sigma level in many healthcare processes, you see mammography screening for breast cancer, antibiotic overuse for infections and bacterial infections and so on, inpatient medication accuracy, you know, they operate at very low sigma, like 3 to 4. And 3 to 4, you might seem that, oh, you know, this is not too far from 6, but this is a logarithmic scale. It's a highly nonlinear relationship, and a 6 sigma or a sigma level of 3.5, you're talking about more than 100,000 mistakes. This is very significant. The Institute of Medicine in 2005 said to address these issues of defects in healthcare, to build a better delivery system. And here better means efficient and effective, safety and quality. We need to invest in industrial engineering. And that's what they did in this report. After this report, systems engineering became very popular in healthcare. And they have defined systems engineering tools into 3 areas: design, analysis, and control. We actually teach healthcare systems engineering in my department. And these topics actually are the building blocks for our curriculum: how to design new systems, how to analyze existing underperforming systems, and how to make sure that those changes in healthcare are sustainable. So it actually looks at the operations management of healthcare, the engineering and re-engineering of healthcare processes. It's a very interesting, very unique topic. In fact, you know, getting a job in a hospital, especially if it's not for profit, our graduates, when they get jobs, especially those who are international students, they're actually exempt from the H-1B quota because they're working as an industrial engineer in a hospital. So that's another reason why this program has become very popular. But again, these are the tools that we use in our research programs and in our academic programs. And the key that we emphasize is the need for data-driven decision-making so that we can have evidence-based, wisdom-based operations, practices of systems engineering, and decisions that are driven by actual data. That's why analytics, data science has become very important in the last 10 years or so. And in 2011, the Institute of Medicine and the National Academy of Engineers talked about the need to engineer a learning healthcare system. And learning here is basically learning from historical data, learning from prior events, from errors, from trends over time. And that's why right after this report, data science and analytics in healthcare became very important. And many of you are probably familiar with big data. You know, right now there are about 10 V's. You know, here I have the older, more popular 4 V's of big data in the area of volume, you know, megabyte, gigabyte, terabyte, petabyte, exabytes, and so on and so forth. Variety, you have text, imaging, you know, clinical data, pharmaceutical data, velocity, the speed at which data is created, and veracity, the uncertainty in the data. And in healthcare, we collect a lot of data. So volume is not an issue. Also, data is generated at a very fast pace. Velocity is high. We also have different types of data in healthcare. So it becomes challenging to operate on. This slide shows you the human body and the amount of data that is generated just from the human body alone. One mammogram generates 120 megabytes of data. One MRI, 150 megabytes of data. One CT scan is 1 gigabyte of data. How do we make sense of this data? We don't want to be reactive. When we have an MRI or a CT scan, the doctor would read it and prescribe a treatment. We want to be able to store these images in an archive or a registry and try to apply advanced data science and analytics to make better decisions, to use machine learning and AI to make better decisions. So the human body is actually a source of big data. So that's why, in our program, we teach both performance improvement, quality improvement, optimization, Lean, Six Sigma, and we also teach data science and analytics. In fact, this fall, we have one course on data science and analytics in healthcare. In 2014, a high-level group of individuals, the President's Council of Advisors on Science and Technology, submitted this report to President Obama's office. They told President Obama, if you want better healthcare and lower costs, you can only accelerate these improvements through systems engineering. They told President Obama that systems engineering is widely used in manufacturing and in aviation. It can help design, manage, measure, improve efficiency, reliability, productivity, quality, and safety. They told the president that many hospitals in the US are applying these methods and they're very successful. But what we need is widespread adoption across the United States. I have truly never seen a discipline get this level of attention. For systems engineering to reach President Obama's office and for him to know about what industrial engineers do, it's a big deal. And this is a summary of all these reports. As part of the follow-up, Erin will send you a copy of the slides and you would have them. And if you are interested in learning more, I'm sure you can view these reports and read more if you are interested. But the key theme in all of these reports is efficiency, effectiveness, safety, timeliness of services, patient-centeredness, and equity. And industrial engineering is all about achieving those. Those are actually the 6 aims of healthcare system. If you go to any system or healthcare system around the globe, whether it's India, China, the UK, Canada, and all that, and you ask them, do you embrace those 6 aims of healthcare? They will definitely tell you yes, absolutely yes. But you can only achieve those 6 aims through systems engineering and health system science. During COVID, this data is September of 2020. Unfortunately, we needed COVID to tell us that health system science, systems thinking, systems engineering matters so much. Because if you think about it, which is a very traditional industrial engineering problem, when demand exceeds capacity, we have a problem. And industrial engineering is all about helping you balance demand and capacity, help you become efficient with your capacity to meet the growing demands. Luckily, our group has been working in healthcare for many years. We have actually started working in healthcare in 2001. So this was not new to us, but it was new to many hospitals in the US and many healthcare systems around the globe. It is, in a way, it's good news, but bad news. The bad news is that we needed the pandemic to tell us that systems engineering in healthcare is important. But the good news is that, we have been doing this and there is enough evidence and we don't have to reinvent the wheel each time. And the good news is that moving forward, people will pay attention to these types of implementations. Our group, as I mentioned earlier, has been doing this for a long time. The Watson Institute for Systems Excellence, which is the research group that was established by our dean, Dr. Srihari. He founded this group in 1989 with the primary mission and vision of the group being focused around working with industry on applied research. This group has 85 students who are fully funded. They get a tuition scholarship and they get a stipend and they are placed in industry as graduate research associates. In healthcare, which is my area of focus within the group, here are the hospital systems that we work with. We actually have today 27 students who are placed in these hospital systems. I'll give you an example, Mount Sinai. When I started working with them in 2012, they had 2 industrial engineers and 2 of my students. Today, that same research group, that same group has 60 plus engineers, project managers, analysts, and so on and so forth. And their leadership want them to grow to about 100 in the next few years. That tells you about the demand for industrial engineers in healthcare. The Mayo Clinic in Rochester, Minnesota, right here. Their group is about 160. Their systems engineering group, today they changed the name to management engineering and internal consulting, has 160 individuals. Again, truly, when I tell you that I have not seen a manufacturing company that has this many engineers, it is so true. And that's why there's so much potential for healthcare systems engineers to contribute to improving healthcare around the globe. The types of projects that my research group has done in healthcare, starting with Dean Srihari, myself, Dr. Yoon, Dr. Wan, Dr. Lam, you know, we all work in this domain. Those are the types of projects that we have done in healthcare. You can see at the bottom here, we have data science and analytics, almost 50%. You know, unfortunately, I have it here as one bullet point, but almost 50% of my work today is on data science and analytics in healthcare. The rest is all about Lean, Six Sigma, simulation, optimization, quality improvement, quality management, and so on and so forth. And the next few slides give you just a couple of examples on each one of these topics. So I won't spend time talking about the list. Instead, I have selected a few examples to share with you. And the first one that I would like to share with you is this pharmacy staffing model. What do we mean by a pharmacy staffing model? Basically telling the director of pharmacy at the hospital how to determine the number of FTEs, full-time equivalents. That's what staffing model is. So it has to do with productivity. It has to do with workload. It has to do with the workload generating factors, and using these workload generating factors to come up with a staffing model. The output of the staffing model is the number of FTEs. How many pharmacists do we need to work in the pharmacy to make sure that they meet patient demand from within the hospital? When we studied this, we found out that to develop a pharmacy staffing model, we have 6 workload generating factors. Those are basically the tasks or functions that are performed by the pharmacists. We need to know how much time is spent on each one of these activities. These are the formulas, the equations, to calculate this time. Some of this data is available in the system, so that's a good thing. We're happy about that. But some of this data is not available in the system. So that's why we have to revert to the traditional industrial engineering techniques by doing time and motion study. So we go through this exercise, calculate the amount of time, and come up with a statistical based model, a quantitative model, and integrate that math behind that model in a graphical user interface, in a GUI, where the pharmacy director at the local hospital can have a menu of the hospitals that they are working with. They can click on the hospital name. It will open up a spreadsheet, and then it will run the math in the background, and it would tell the hospital director, the director of the pharmacy, how many pharmacists they need for every inpatient unit. And again, here we're talking about very large hospitals, 300 beds, 400 beds, 200 beds. This hospital system actually has 4 hospitals. So it's a very large health system. That's what we call health system in the US. A health system has multiple hospitals, and our local health system has 4. And knowing the minimum, the maximum, and the average FTE requirements is what we are aiming for in this particular project. This is one example of a project that we have done. Another example is what we call door to balloon time. If any of you, have a father or a mother or an uncle or an aunt or a relative, a brother or sister who works as a doctor, please ask them about this door to balloon time. They will know, especially if anybody is working in cardiology and in catheterization labs, they will know exactly what door to balloon time is. This is basically that if a heart failure patient shows up at the emergency room, very quickly, they have to be transported to the catheterization lab for them to do some work to be able to save their life. Simply speaking, they call it door to balloon time. Door is basically the emergency room door. Balloon is once they get to the catheterization lab and they have things that go into their blood vessels and open up blockages and so on and so forth. According to the American College of Cardiology, the American Heart Association, if you have 100 patients that show up at the emergency room, more than 75% of them should get to the catheterization lab in less than 90 minutes. So if you think about it from an engineering perspective, this is a speed problem. This is a velocity problem. We need to move the patient quickly. But at the same time, from an outcomes perspective, from a quality perspective, this impacts the mortality of these patients. If your hospital does not meet this target, this means that your mortality is not good. So that's where the role of industrial engineering comes in, because our focus is based on efficiency and effectiveness, based on speed and quality, the velocity of the process, and the outcomes of the process. So we've actually done this work with our hospital partner, and we were able to help them achieve the standard. Otherwise, their mortality will be suffering, and a lot of people will be dying because of this, or it will take them a very long time to recover. It's not only about mortality, but it's also about the quality of life after this incident and the time to recover. This is another example that I wanted to share with you. Another example is lean thinking in hospital design. The way architects design, if you go to any architecture firm, they build the layout, and then the layout will dictate patient flow, will dictate process flow. This is actually not a good strategy. The patient flow, the process flow, should serve as an input to the architects when they design layouts. This is what we call evidence-based design or process-driven approach to hospital design. So I had about 6 students working with Virtual Health. This is a hospital in New Jersey, to try to use lean methodology, working with the architects to design this hospital. Very successful project. This is the first hospital in the US to be built based on the principles of lean. Back then, we called it lean in hospital design or process-driven approach to hospital design. Today, it's known as evidence-based healthcare design. This is another example that I wanted to share with you. In the interest of time, I'm going to skip, one of these, some of these slides, and show you maybe this slide about some of the simulation models that our students have developed to study emergency rooms. This simulation was done using a software called Simio. And you see this is the dashboard of the simulation model. This shows you the number of patients that arrive at the emergency room, the number of patients that leave without being seen. This shows you the processes that the patients go through when they arrive, the intake process of these patients, and then all the other processes that they go through. And if you look at this flowchart is actually very complex. all the way until they are moved to the inpatient units. And then later on at the end, they get discharged. Of course, we have fast forwarded the simulation and we're running it at a very fast speed. But this shows you the complexity of healthcare processes. And I'll go back to the slide to show you the patient pathways when they arrive to the emergency room. You have seen it in the simulation model, but again, this goes back to the patient journey map that I showed you in slide number 1. The complexity of healthcare processes and why industrial engineering is needed to solve these problems. The next slide I want to show you is analytics and data mining. In analytics, we have to do quite a bit of work, starting with building the data warehouse in a hospital so that we can do what we call the descriptive analytics, building the data warehouse and having a platform where we can do dashboards, reports, business intelligence, knowing where we are today and where we were in the last couple of years. And next is going to predictive analytics and prescriptive analytics. The complexity of the methodology increases as we go up. But here we have techniques like optimization, decision trees, mathematical modeling. Here we have data mining, machine learning, AI, regression models, simulation. We actually teach a lot of these in our curriculum to our students in industrial engineering. This is not your typical industrial engineering department, but we always look for ways to enhance the skills for our students. And I'm going to show you just one example, and then I will try to conclude this session in the interest of time. I would like to show you this example of what one of my students have done at Mount Sinai Hospital. This project was actually looking at patient no-shows and patient unpunctuality. Believe it or not, there are a lot of scheduled patients that actually do not show up to their appointment. We did a project at a dental clinic. We found out that 30% of the patients do not show up for their appointment. I was surprised. I was shocked actually that out of every 10 patients, 3 do not show up. So you end up with these expensive dentists who are idle for 30% of the time. That's a problem. In physical therapy, the patient no-show rate is 22%. Occupational therapy is 18%. Speech therapy is 17%. So just imagine, out of every 10 patients, 2 do not show up. And then you have those physical therapists idle. So we studied this problem, but we also wanted to predict no-shows, but also look at predicting punctuality. As we know, things usually don't start and end on time. If a patient has an appointment scheduled at 1 p.m., some patients will show up at noon or at 11 a.m. They want to show up early. Some patients will show up late. If you go to Manhattan, for example, some of the hospitals in Manhattan, because of traffic and delays in the subway and the train system and so on, some of them will show up, plus or minus 5 to 30 minutes, early or late. So we wanted to study the impact of no-shows and unpunctuality on the schedule. So we actually made this as a scheduling optimization problem that gets input from a machine learning model that predicts 2 things, unpunctuality and no-shows. And then those are fed into the optimization simulation model, and then we come up with an optimal schedule that accounts for no-shows and accounts for punctuality. The airline industries do that. They do overbooking. But what we are proposing is an intelligent overbooking model that intelligently knows the no-shows and punctuality and optimizes the schedule in that manner. That's what we're aiming for. And this was actually one of my students' master's thesis. And I've had many people from India, from biomedical engineering background, computer engineering background, computer science background, that come and join my research group and we fund them as research associates because they're very interested in machine learning and AI in healthcare, and they've used this as an opportunity to work with hospitals to develop these models, and then they get excellent jobs. Process mining, we talked about in the previous slide, is data mining. This is data mining. But we also have process mining. As industrial engineers, process mining is also very important to us. And then process mining, that can be used, by the way, this can be used in manufacturing and in any industry. We mine event logs. And this is a screenshot that shows an event log. The event log has the timestamps, the activities, the resources, the cost. And instead of mining static data, we mine sequential time-based data sets. That's why it's called process mining, to discover issues about the process so that we can control the patient flow, look at the way the organization works and the resources, look at the different cases and their properties for different diagnostic related groups or lab tests or x-rays, and also look at the timing of the events and see if there are issues that we need to worry about. And process mining can be used for discovery in processes, for conformance, to make sure that what we do is in compliance with the evidence-based pathways, and also can be used to test different what-if scenarios. And in process mining, we actually have many different types of algorithms that we can use to mine those event logs to come up with interesting insights about the process. And I will show you an example of a hospital that actually used this. This is a health system that has two hospitals, Hospital 1 and Hospital 2. Those two hospitals, they treat stroke patients. If somebody comes in with a stroke, they treat them. And this is the process map at each one of these hospitals. Notice that it is similar, but different. When process mining was used by these researchers in 2008, they found out that Hospital 2 performs hypertension therapy earlier in the process and more than Hospital 1. Hospital 1 has processes that are more compliant with the recent evidence-based care pathways. So notice that they're not consistent. One is more compliance, the other one does, things in different sequence and more than the other. Which one is right? Obviously, the one that is more compliant with guidelines is the one that we want to go to. So we need to work with Hospital 2 to fix their processes to make sure that they are in compliance. And those are the kinds of things that we can get from process mining. And finally, I want to share with you that at Binghamton University, we were able to integrate all these research activities into educational programs, into master's programs, PhD programs. So our students can actually pursue degree programs and concentrations in the area of healthcare systems engineering. So we don't only do research in healthcare, but we also teach these programs. Those are the courses that we teach in healthcare systems engineering. We teach a lot of courses, and that's why we were able to create a separate engineering degree in healthcare systems. The significant career opportunities for our graduates are listed on this slide, from hospitals and medical centers to government and public health organizations, to pharmaceutical companies, health insurance companies, architecture firms, and pharmacy companies, to manufacturers of healthcare products like Regeneron and so on. Those are the job titles for graduates of healthcare systems engineering. Again, an industrial engineer in a hospital is not uncommon. In fact, it's becoming more and more common each and every day. And our students get excellent jobs, excellent starting salaries. This shows you that our students, their average salary is in the 85,000 to 115,000. And those are some of the hospitals that hire our students. So a lot to look forward to when we look at the healthcare of the future, hospitals of the future, hospitals of tomorrow, with precision pills and personalized medicine using analytics, looking at smart technology, smart beds that can detect falls and hopefully prevent falls, putting the patient in control and making sure they know their itinerary in the hospital and they know the progress of their journey in the hospital, making sure that the patient has a health display based on advanced analytics. Also looking at the future of biomanufacturing and 3D printing. There's a lot to look forward to. Again, as I mentioned, healthcare is very complex in terms of processes, systems, and people. And we need to keep this in mind as we design the hospitals and the health systems of the future. And with that, I would like to conclude my presentation and invite you to stay in touch with our department. Please follow us on Facebook, Instagram, Twitter, on our LinkedIn page to stay in touch with our department, to learn more about our university, about engineering programs, and the kind of work that our students, faculty, and staff do in healthcare, manufacturing, supply chain management and logistics, machine learning, and AI. And again, I would like to thank the Vice Chancellor and Dr. Sogo for inviting me to deliver this presentation to the faculty and students at VIT BHOPAL. And I hope that this will serve as an initial introduction. And we look forward to having other webinars and to continue to stay in touch with our colleagues at VIT BHOPAL. And hopefully in the future, I will be able to visit you in person and spend more time to talk about these activities and maybe give a day-long course on healthcare systems engineering. Truly, what we did today is just barely scratching the surface, just to introduce you to systems engineering in healthcare. And again, my contact information is listed on the slide in case anybody has any questions or require any follow-up. And with that, I would like to thank you again and turn it over to Dr. Sogo for the next session.
So I would like to propose the formal vote of thanks for this webinar. So at the outset, first I would like to thank our management, Dr. G. Vishwanathan, our Chancellor, and our Vice President, Mr. Shankar Vishwanathan, and our Assistant Vice President, Ms. Kadambari S. Vishwanathan, and our Vice Chancellor, Dr. U. Kamachimudali, for his constant guidance and encouragement in establishing this memorandum of agreement. And also I would like to this opportunity to thank Professor Srihari in helping us out with this memorandum of agreement between Binghamton University and VIT BHOPAL, and Professor Kashavne for agreeing to deliver this wonderful speech and insightful webinar about the healthcare system and how the industrial engineering is making this impact in healthcare system and what will be the future of healthcare systems. And also, I would like to thank all the faculty members and deans and student members who have joined this wonderful webinar in this evening and morning in New York. Thank you very much, one and all. I hope to meet in another occasion where we will have more and more webinars from Binghamton University, and we are looking forward to further collaboration and further insightful webinars from Binghamton University. Thank you, one and all. Thank you.
Thank you. Thank you very much, Dr. Sogo, for the nice introduction and the concluding remarks. As I mentioned, definitely the sky is the limit here. And some of the students were asking about supply chain. So the internal supply chain, the external supply chain has significant influence on the success of the healthcare system in achieving its objective. And those are topics that we can definitely address in future seminars. So I would like to thank you again, thank the Vice Chancellor, thank all the deans, the HODs, the faculty, and the students for joining us today in the last 1.5 hours to learn more about this topic, and definitely look forward to the future sessions.
Thank you, Dr. Kasavani, for joining us.
Thank you, sir. Thank you very much.
Thank you.